Okay, we're back. Now let's look at a first organic device structure. And let's start with OLEDs, organic light emitting devices. Now this is the most basic one you could make. This is a metal polymer metal device where the electrodes act like PN junctions for injection of electrons and holes. I'll explain that more on the next slide, but it's a really simple one-layer device. Okay? So here's your emission layer, there's the molecule, and then I've got these two electrodes which inject electrons or holes. So looking at this device, here it is emitting red light. There's a couple interesting things. Look at the table here. Here's the band gap energy, 2.1 electron volts, which is for red light. That makes sense. Look at the mobilities. They're tiny, so much smaller. You know, for silicon and gallium arsenide, we get into the hundreds or thousands. And this is 10 to the minus 4, 10 to the minus 5. This is tiny mobilities compared to that. So, what's that mean for us? Well, look at this device, okay? These devices are, 50 nanometers, 500 angstroms, 50 nanometers, to 200 nanometers thick, which is as much as 20 times less than the width of a BJT base, which was already really thin at 1 micron. So these are really thin layers. And look how much voltage is required to turn this thing on. Well, that tells you one of the challenges you have with organic semiconductor devices. Their mobilities are so low that to get the amount of current you need through them, even for very thin layers, you need a lot of voltage. And that's a challenge because if you make a layer that's only, 200 nanometers thick and you have to apply 10 volts to get the current started, if you have the tiniest speck of dust, that will cause a short between your electrodes and cause this device to blow up in a puff of smoke. And so that's one of the challenges they've had that has slowed adoption of OLED displays. Now here's a bit more advanced OLED device structure, which is metal, polymer, polymer, metal, and it's been optimized for carrier injection. So how does this extra layer help? This is the original layer, which is light emitting, and we put one extra layer in here. And let's see how it helps. And let's also look at how the electrodes inject electrons or holes. So, first thing, here's the light emitting layer here. Here's my cathode, which injects electrons. The metal, you can see, is closer to the conduction band here, so it will inject electrons onto here. So I get my electrons here waiting to recombine. My anode is a metal with a work function that's way down here compared to the cathode. And so it lines up down here and it's able to inject holes, which can make it here and recombine with electrons. This additional semiconductor, organic semiconductor layer was added for two reasons. One, it helps the hole injection. Instead of having to jump all the way this energy from here onto top of here, I can step it twice, which is much more probable than trying to go the whole distance. So it'd be like me asking you to jump from the floor onto the top of a chair versus 2 chairs high. Your probability to get to 2 chair high would be much lower, much more difficult, right? So make it a step to make it easier. The other thing this does is that the electrons coming this way get stuck because of this barrier, and they just sit here and wait until the holes come here. So this forms an electron blocking layer as well to hold electrons right here until the holes come and they can recombine. So you can start to see how we use band gap engineering to start to build these devices up. Now the anode is typically made of something called indium tin oxide. It is indium oxide, a wide band gap semiconductor doped with tin oxide, 10%. What type of semiconductor? Again, it's a wide band gap semiconductor with a band gap that is so wide that it looks transparent like glass. So that allows me, when I dope it with tin oxide at 10% of its weight, which is a lot of doping, it becomes conductive enough that I can use it as an electrode, but the band gap's so wide that visible light goes through it, and now I've got an electrode I can use on top of organic light emitting diodes and use for display applications as well by depositing the electrode on the glass. So this is a bunch of glass sheets which have been deposited with this indium tin oxide electrode material. Let's go even more advanced here. You should be able to answer all of these questions here. So, first off, why do we have a hole injection layer? Well, here's the anode, injecting holes, same thing. Basically, to make it so you don't have to jump up too high here, you can do it little by little, essentially, to help get the holes where they need to go. Why do we have a hole transport layer? It does the same thing. Here's my emitting layer, and so this is injecting, meaning getting from the anode into the device. Hole transport is helping transport then from the injection layer to the emitting layer, because that's still a pretty big step there. Okay? What else does the hole transport layer do? Well, it only transports holes, because look at the lineup here for the electrons. The electrons see a significant barrier here. So this is a hole transport layer, meaning holes can go this way, but electrons see too big of a barrier, they get stuck here. Why do we have an electron transport layer? Well, it basically is doing the same thing. It's helping me get electrons in this direction. Electrons can easily go this way if I forward bias this, whereas holes see a barrier. It doesn't transport holes, it only transports electrons because it creates a barrier there. Why don't we need an electron injection layer like we had a hole injection layer over here? Because the barrier here is already low enough. So if I wanted to forward bias this thing, I would put voltage to move this up, voltage to move this down. That would mean positive voltage here, negative voltage here, and I would start to see light emission coming out of the emission layer for this device. And again, the best devices are even more complex. The commercial devices have even more layers of this with all these different semiconductors optimized to help you get what you need in terms of the device working. And the workhorse material in this industry is ALQ3, shown here, which is a green emitting material. But how do you make full color displays? Well, let's start to look at display technology, and you'll see where semiconductors come into play as well. Before I talk about OLED displays, let's talk about an active matrix display based on liquid crystals. And so every pixel in a liquid crystal display is like a little light valve that switches between white and black, and then I put a color filter on top of it to make it look colored. So I just basically add some kind of red, green, or blue pigment. So all of these pixels are white and black liquid crystal shutters, and on top of them they put pigments which filter the light to become red, green, or blue from the backlight, which is white light. Okay? So the question is, how in the world do you electrically drive a huge array like this? Imagine if I have a typical LCD display which has 1,000 by 2,000 pixels. Well, I would have, if I have 1,000 by 2,000 pixels for a display, let's say I have 2,000 this way and I have 1,000 this way, that would be 2 million pixels, right? If you multiply all the rows and the columns together. Well, I cannot bring 2 million electrodes into a display and control them all. Your LCD TV or your smartphone would have a huge wire bundle on the back of 2 million wire connections going to every single pixel. And so what you do instead, you use something called active matrix addressing, where each pixel is a capacitor and is at the intersection of multiple columns and rows, and each intersection forms a pixel. So this is kind of like when we had memory, remember? It's a very similar design where basically I have a transistor for each pixel. So this is the pixel here, this is the pixel, and this here is the transistor. So that's my transistor in this case. And if I want to write this pixel and only this pixel, I will put voltage on this row, which turns this transistor on and only lets voltage coming up this column to then set the pixel level to a certain level of black or gray in terms of its transmission, black or white in terms of its transmission. And how you do this is you basically write the first row, send up all the data, you do the second row, send up all the data, third row, etc., and you scan through that 60 times per second to create video motion. Now, these transistors for a display, like a liquid crystal display, are called thin film transistors. Why are they called thin film transistors, or TFTs? Well, the hint is, think about the substrate. If I have a silicon wafer, I can diffuse in dopants and I can create my transistors in a thick substrate. But for a display, these are fabricated on glass, and so the transistors themselves are deposited as thin films on top of the glass to make the transistors. You'll see that on the next slide here. So here's two types of TFTs. This would be my glass here, Okay, here's my glass, and you've got what they call staggered and coplanar, top gate and bottom gate. Here's your semiconductor layer, okay, and you could see a couple regions for source and drain. So you want to get current flow between the source and drain. Here's your gate. Here's your oxide. You put a voltage on here, you could create a channel in there. There's many different 4 variations. You could figure out easily how 4 of these work. In this case, the gate is buried underneath, and then here's your source and drain. Here's the semiconductor material, and I put a voltage here to get current through there. There's my insulator right there. And so you could look through these. I won't go through these in detail, but these are all thin films that are deposited and built up to create different types, these 4 different types of transistors. So you notice that it says amorphous silicon. Why is it amorphous silicon? Why not crystalline like we had for regular diodes and MOSFETs and stuff like that? Well, again, our substrate is glass. It is an amorphous material. You cannot grow single crystal silicon on anything other than a crystalline substrate which is matched to it in terms of bonding. So when you deposit the silicon, it ends up being amorphous, which lowers its performance, but it's good enough to drive these pixels here. So this is active matrix for liquid crystal displays, where each little liquid crystal pixel acts like a capacitor. The more you charge it up, the more light transmission you get through it. But why will this not work for OLED displays? What type of circuit component do we need instead? Well, for OLED displays, we know it's a diode here, and we have to drive current. So it's not like I can just come here and basically put a voltage here and the OLED will stay on. It'll dissipate the voltage very quickly. So I need to keep current flowing through this, which doesn't allow me to go from row to row to row to drive this in a matrix. So for OLED displays, each pixel has not this, which is simple, but it has a small circuit, which is a current source or a current driver. And so how this works is that here's my row. I turn a row on, okay, which turns this transistor on. I can then send data up a column, which will then go through here, set a voltage level, which is stored on this capacitor. I set my voltage level here. Then I turn my row off, which shuts this off. The voltage level stays here, charged on this capacitor, which keeps this transistor here in a current mode that provides a certain current from VDD through the circuit and powers the OLED. So once I've set the voltage here, it stays charged up with this capacitor. That voltage keeps the MOSFET on because it's a capacitor here, so there's no discharging of the voltage. And then that current will keep going from VDD through the OLED, which is the diode, and keep the OLED on until I come and write the row the next time, where I turn the row back on and I write a new voltage level to change the brightness of the OLED the second time through the amount of current flowing through it. One of the challenges is if you have a current-driven device, you need higher mobility, right? Because you're driving current all the time. You don't want to have too much resistance. And so if you look at things like amorphous silicon, the mobility is really low, 0.5 to 1. Again, silicon crystalline is in the hundreds. You could do polysilicon, which has higher mobility, but that has to be deposited at 450 degrees Celsius, which melts most glass. You could use organics, like we talked about, which can be deposited at low temperature, but their mobility is really horrible. And so what people are looking at is a new material system, indium zinc oxide, which can be deposited at low temperature on glass, and which has mobilities of 10 to 50, which is much better, and allows you to have the current flow you need to really drive OLED pixels with a high amount of current and get a good brightness for these devices. So, LEDs are coming, but it's taken forever. And so there's been multiple articles over the years that said stuff like active matrix OLED TV sets are coming really. Meaning that we've said it before, but they're not there yet. So this is from 2011. They are coming, they're finally hitting the market, but they've had a lot of challenges because these OLED materials, they're so thin and they have a decent amount of voltage on them that it's easy to get electrical shorts, and the materials tend to degrade over time as well. While we're talking about organic thin film transistors, obviously OLEDs are organic, but the TFTs that drive them cannot be organic. Again, the mobility is too low to drive the current levels we need to get the brightness from the LED. However, organic TFTs are okay for displays that are capacitance-based like liquid crystals. Because you don't care if those, especially ones where you don't care if the switching speed is slow. And the advantage that you get is that although you switch slower, these devices can be made rollable because you're putting all your transistors on a piece of plastic. And so one example of how you make a rollable display is e-ink, which basically has a charged ink where if I put for example, I'll put a positive voltage, I'll put a negative voltage here. So I'll put negative voltage here and I'll put positive voltage here. That attracts the negatively charged black pigment particles in a fluid here to the top and the white ones to the back, so that area of the pixel will look black. I could do the opposite, put negative here, positive here. That will reverse the positions of the particles. Then you see white at the front, and you can see white in the appearance. And the key point is that these things switch slowly, which is okay for an organic TFT, which allows you to basically put e-ink on a piece of plastic and make something like this rollable, foldable display here. And so some of the first foldable technologies that might hit the market may be based on organic transistors and slow switching devices. But it's going to be a while before you can see something like a OLED display, which requires a lot of current to appear in some kind of device which looks as big as an iPad, but which you can fold up and put in your pocket. So what about organic photovoltaics? Well, you can also use organics to harvest energy from the sun. This is a simple Schottky diode approach. I won't go into a whole lot of details, but here's the metal, here's the semiconductor side, here's another metal, and here's my depletion region here. So light comes in and you get your carriers separated. A more sophisticated version is you start putting in multiple layers to basically get your depletion region here. I'm not going to go through this in detail because the terminologies they use are very different than what we use, but you're doing the same kind of thing with depletion, and you have light come in, separate, charge, you collect it as well. So here's an example of a company that has been working on organic photovoltaics. Some of the advantages they talk about is it's really lightweight, flexible, and it can be really low cost. You can make this stuff in rolls and sheets and put it on buildings, backpacks, you name it. And they say they use a tandem cell, which has complementary absorber systems. So what does this mean by complementary absorber systems in a tandem cell? Well, what this means is that there are basically two layered photodiodes, just like we had for multi-junction solar cells. And when they say complementary absorption solar cells, they mean if this is my spectrum of sun, one will capture one portion, the other will capture the other portion, meaning that they're complementary in terms of how you stack them up, and this will absorb the higher energy ones, this will absorb the lower energy ones, and then you can capture more of the wavelengths from sun in the solar cell and convert them efficiently to energy, just like we did with multi-junction solar cells. And they've had a lot of press. Here's a company, Konarka, 8.3% efficiency, which is actually not bad. That's about half of silicon, right? So that's not bad. And there's all these sort of really cool demonstrations, make them low cost, laminate them to the side of a building. They can be partially transparent, so you can put on a window and still see through. You could basically have this large panel which you roll out of your backpack, lay out on the lawn, and then you can charge a gaming device, put it on top of a bus stop, and light up a something like this. There's all these advantages, but, well, I'll get there in a second. I'll get to the but in a second. And if you look at this is the product they offered for a while called Power Plastic. And it's interesting, you look here, same stuff we talked about for photovoltaics, open circuit voltage, short circuit currents, okay? And so it's very similar in terms of the same things we talked about for silicon. But here's the but. Lots of excitement about OLEDs and OPV, but they keep struggling to commercialize. So this is that company Konarka with all those cool products. 2012 they enter liquidation, which is a term in Europe for bankruptcy. And so they said organic company demonstrates that $200 million investment and a Nobel Prize are no guarantee of commercial success. And so these technologies are coming, but there have been difficulties. Again, one success is OLED displays in small phones like smartphones, and eventually at some point they might become more economical for large area applications as well. One of the really hot developments going on these days, and this is the company I've been following, which I think is really exciting, called Thin Film. They are now using inks which have organic semiconductors in them, which they can print on a conventional roll-to-roll press on things like plastic and paper, and they're printing both memory and logic. The big breakthrough they had is they've been able to basically get complementary logic, both kind of like NMOS and PMOS, which when you have both, then you can create inverters, and NOR, XOR, etc., and memory, and start to make logic circuits that I can print by the mile and make it so low cost on a roll-to-roll process that I can cut these out and put them in all sorts of products like smart cards. Imagine sensors that track the temperature. You buy a thing of chicken at Kroger's and you look at the label, and the label has a temperature sensor and a digital display that tells you if it ever went above a temperature where the food could go bad. And so there's some really exciting developments in these types of circuits. These are low performance, meaning they do not switch fast, but they could be made to be very low cost through just simple printing technologies to use to make these technologies. Other uses of organics, I'm not going to go into a lot of detail here. Check out this video. This is basically a waveguide that's edge lit with UV light, and then we put fluorescent inks on the top that are organic, which emit red, green, and blue light. So the light waveguides through this thing like it does an optical fiber. It gets coupled to the inks, and the inks are transparent such that you can make transparent signage. And here's the intensity versus wavelength. Here's the pump. It's a gallium nitride LED that emits 400 nanometers. And then here's the blue fluorescent material, organic green fluorescent material, and organic red fluorescent material that convert the high energy UV light down to visible light. So let's do some final review. For this OLED structure, you should be able to answer all these questions now. And another question for you is, how do you drive electrically an OLED display? What do you need to do it?